All right, well, last time I think I told you more information about F equals MA than you would ever really want. But today I want to go on and talk more about the particle in a box program. Let me get the share screen going. So starting off here, making a constructor for a particle. Our constructor is going to have a color, a position, a velocity, and a mass. And we're going to make an array of these particles. Starting off with this, we're assigning mass, color, position, and velocity to our different particles, all basically with random numbers. And we're loading them into point coords and point colors, which we're then setting up various buffers to send to the GPU. To update the particles, we're going to form a delta that is our dt times the particle velocity. Use that to update the position by adding that delta p to our particle position. Doing the same thing for the delta v. We'll scale the vector forces that will come from someplace by dt over particle mass. That's the F over m. And then update our particle velocity by adding that delta v to the particle velocity. We'll check for collisions. I'll show you that in a second. And because we're doing this in the CPU, we have to send these new point coordinates to the GPU. We're calculating the trajectories there with Euler finite steps. So for collisions, one way we can do it is with a repulsive force. Another is to check for penetration and calculate where the particle would end up. We'll have two types of collisions, elastic and partially elastic. In an elastic collision, which is where the angle of incidence is equal to the angle of reflection, the normal component of the velocity reverses and the tangential component stays the same. With partially elastic, we have this restitution where they bounce half as much. We got a kind of picture of this. We detect a particle over here. If it had an elastic collision, it would have bounced to be over here. If it has some coefficient of restitution, it doesn't bounce as much, so it ends up here, going off at a different angle. You notice that in inelastic collisions, the angle of incidence and the angle of reflection are not equal. Light bounces elastically. That's why we have that. So here's a little code fragment for detecting collision for particles moving in the plus x direction, hitting a wall at x equal L. We're going to reverse the velocity scaled by the coefficient, and we're going to move its particle out to be a distance in front of the wall that's coefficient times the position behind the wall. I need two functions here for collisions and forces. The collision function is going to take care of things colliding with the +1 side and the -1 side. And we're scanning over the X, Y, and Z positions for these. A little test to make sure they don't get outside the box. Forces, we're going to have three components: gravity, repulsion, and attraction. Zero those out to begin with. The gravity is in the y direction with a negative amount. And here, what I'm doing is I'm using the inverse rotation matrix to rotate my gravity force so that it points down as we modify the box. The gravity will always point down even though we rotate the box. For repulsion, a weak r to the sixth. Here's the distance between the two particles, then cubing it and then multiplying it again makes it a sixth. And so I'm scaling that vector t, the vector between the two, by some constant over the d2 that is the r to the sixth. And I'm accumulating that into my force r that I'm going to add up. You don't need to do this, but if the distance is ever equal to 0, I'm just putting a random vector force out here. One other thing, to avoid dividing by 0, we often soften the potential by making dt no smaller than some particular number. This way we don't get really tiny d2s that produce spurious results. The random vector we could generate like that. Attraction is exactly the same, except here we have now just d squared. This is an inverse square. Also, it's negative, whereas the repulsion was positive. And again, I'm doing this random vector. And then we add them all up. We add force G to the addition of force R and force attraction. Let me switch here now to particles in a box using ThreeJs, since I assume many of you will follow that approach. With the ThreeJs system, we're making a particle system, system 1. We're using a snowflake material. This is the author's code, by the way, that is provided in his chapter 10 section. This doesn't have rotation. It has, you can change the speed of them, some other kinds of stuff. It does have repulsion and gravity, and restitution, but it doesn't have attraction. So let me show you kind of what we're aiming for with our homework problem. This is the author's code version. And so now I have a trackball interface on this that I can rotate my cube. I have the ability to turn on gravity so that the particles kind of fall. Let me toggle restitution so they run out of speed. So these particles are falling in the down direction here as they go. And I can toggle on repulsion, attraction. Let me toggle on repulsion so that they stay away from each other. So they're settling now down to the bottom, and we can do attraction too, which is going to make them suck towards each other. But of course, I expect you're going to be doing this with ThreeJs, since it's much more fun. And for ThreeJs, our version kind of looks like this. I've got my box. I'll show you this arrow helper, which I found really useful for getting the orientation of the gravity correct. But I've got these different particles. I can turn on gravity and they fall. I can turn on attraction, turn on repulsion, and set restitution to be an inelastic collision. So, and of course can rotate this thing and the particles fall in the down direction here, which is what I want. So what am I doing in here? Well, I'm creating a particle system, system 1, with various textures, sizes, transparency, opacity, size, attenuation, and color. And this create system goes through and sets all that up, setting the particle size, whether they're transparent, what their opacity is, what textures on it, what kind of blending we're using, and so forth. And in this creation, I'm going through the number of particles that I want to generate, generating random x, y, and z, and random velocity x, y, and z, all of which are part of my particle. My particle contains positions as well as velocities, and these are all loaded into the geometry vertices, into the vertices of my geometry that is created here with particle system geometry and that material that I made up above. That arrow helper is a nice little trick. The arrow helper was very helpful in orienting the down direction as I rotated the object with the trackball. And here I'm getting a direction. I'm using a copy gravity. And let me just show you why I had to do this. This is a nightmare, but this is a funny feature of ThreeJs with vector3 objects. The reason I did this, rather than just assigning dir equal to gravity and then normalizing it, is that at some point later, when I normalize gravity, this, say in the repel function, oops, this is not at the beginning. With ThreeJs and JavaScript, I ran into a lot of problems debugging this thing. If I have a vector that's got 1, 2, 3 in it, and I just do a v2 equal v1, and then I normalize v2, we would expect that v1 might not be changed, 1, 2, 3, but in fact it is. v1 is also normalized when I normalize v1 that is assigned by this simple copy here. And the reason for this, and you can look at this website that talks about it in a great deal of detail, but the bottom line is way down here at the bottom. Objects are copied by reference rather than by value. When we copy by value, we make a new memory location and we copy the value into the new memory location. When we copy by reference, all we do is give them the same memory location. And so doing this, v1 and v2 have the same memory location. And so when I normalize v2, I'm also normalizing v1. The proper way to do this is to use the copy function, this one. So I make v3 a new vector 3 with nothing in it, and I use the vector3 copy method. This is going to copy v1 into v3. And so v3 now is a copy with its own address. And what we do to v3 would not affect v1. And so all of this, and this is why in particle in a box, I'm doing this dir as a vector and using copy and then normalizing it, because if I did this, gravity would be normalized as well as dir. This crops up other places I'll show you later. What a nightmare. So back to my particle in a box here. For my arrow helper, I'm getting the direction. The reason being that with arrow helpers, the direction has to be a normalized vector in the one direction. I also found for some reason I have to use a negative box size to get the vector right. And then we create the arrow helper and add it to the scene. And that's the little thing that I've got here. Oops, not that one. That's the little thing that I've got here in this. That's the arrow that I've got here that always points in the down direction, even as I move my trackball object around. So all of the physics is done in the update system that's called in the render function. The render function is pretty simple. It just does the stats, does the trackball, updates the system, and then calls for a new frame. But in the update system, I'm going to get this temp gravity, again, that I'm using the copy thing because I'm going to fiddle with it. I'm going to change the temp gravity, and if I did temp gravity equal gravity, everything gets screwed up. And this was the bug that I wrestled with for hours. I have to unorient this vector to keep it always pointed down in my scene. And I do this by setting the arrow helper's rotation, that's a quaternion incidentally, by using the set from rotation matrix M, which is the camera's world matrix. Local gravity, I'm going to transform its direction using that camera's world matrix, so that my local gravity points in the same direction as this arrow that points down. I'm going to scan through all the verts of the system's geometry. So here's verts is the system geometry vertices. I'm also allowing for the possibility that I'm going to do more than one time step per frame, often because we have to keep delta t small, but we don't want to render every delta t time step. We have this iterations that goes through it, several iterations. I think I'm actually using 100 iterations. So then I'm going through all of the different verts, and I'm here setting v equal to verts. It turns out this is okay here. I'm going to zero out the force. If I'm using gravity, I'm going to set that G to local gravity, the one that's been turned to point in the direction of the arrow, and I'm going to add it to the force. If I'm using attraction, I'm going to call an attract function, passing it the V that I'm using and the array of verts that I'm going to have to go out and touch, and I'm going to add that to the force. And again, repulsion, I'm going to call repel. Notice these are order n squared kind of functions, and so not doing them if I'm not bothering to calculate that force is an important efficiency. So once I've accumulated all my forces here, I can just go through, update the velocity with force times dt, and then update position with velocities times dt. This incidentally is the Euler-Kromer method, since I'm using the updated velocities as soon as I have them available. Collision testing, I had to do X when it hits the right-hand wall, X when it hits the left-hand wall, V when it hits the top and the bottom, and Z when it hits the forward and the back. And then I don't think this is actually necessary because of the shared memory location, but just to be sure, I did that. Attract looks very similar to what I showed you with the other code. I have the vertex that I'm testing, and the array of verts. I'm catching v1 as a new vector with vx, vy, and vz. This is so that if I modify it, this is making a new copy of it. I could do it with copy too, but I did it this way instead. zero out the force, go through all of the other vertices, form V2 of them, again using this creation trick, forming the vector between them with just explicit differences between each of the components, get its length. This is not the same as the length up here. This is the magnitude of the vector. If it's greater than 0, then I square it, add that little softening in, form the factor that I'm going to multiply this vector by, minus something over d squared, and then multiply that vector by that and add it into the force. By testing for d greater than 0, I'm eliminating the possibility of testing the v with it itself in the Verts array. And so I'm never A, dividing by 0, and B, I'm not testing for the force of the thing with itself. Repel looks almost exactly the same. Except of course, the D2 here is d to the 6th. We cube it and then square that and then store it back into D2. And notice here, this is positive. So the rest of this is, I won't go through. This is just a simple framework that you can use to get started. It has the basic framework for you, and you can get started with this. So dealing with the nightmare and the particle in the box, next time I'll start talking about fractals, which our author seems to be obsessed with. But here's my version of what the homework might look like, with the ability to turn on gravity, turn on attraction, the particles, and turn on and off restitution. And then, of course, the particle size attenuation that was left over from the snowflake thing. So I'll end the share screen here and finish this lecture. I'll see you all in class. Talk to you later. I'm stopping recording now.